Thank you. Thank you for having me. So yeah, I will indeed talk about a certain inverse theorem for polynomials. In some sense, the simplest one that you can think of. And all of this is based on a joint work with my fantastic student, Alex Cohen. So I'll start with some general context about the problem and then move on to what we did. So you can put the whole thing, the whole question under the umbrella of the structure versus randomness dichotomy in math, where in different areas of math, you often see this dichotomy that the objects in question, whether they are groups, graphs, functions, or whatnot, they tend to either behave like the random object, or else they're structured in some useful sense. So we're going to talk about the instance of that dichotomy for low-degree polynomials. And there are standard ways to define randomness and structure for these objects. So randomness is usually defined by the notion of analytic rank, introduced by Tim Gauss and Julia Wolf. So the analytic rank of a polynomial P, so P is a polynomial in n variables and over a finite field F. By the way, unless I said otherwise, all the fields would be finite fields. The question we're talking about is a question about finite fields. So the analytic rank is defined as follows. You fixed your favorite additive character and you just apply it on your polynomial and average over all possible inputs, normalized. Okay, so in particular, if you look at zeros of the polynomial, okay, so inputs x such that p of x is 0, then chi is going to be, right, chi of 0 is maximal, is 1. And so this average here gives the most weight to zeros of the polynomial. Generally speaking, it measures the kind of how well distributed, or maybe I should say how biased the polynomial is when you view the polynomial as a function. Okay. So a quick sanity check. When you take a random polynomial P, then you would expect this sum of chi of P to have lots of cancellation. So it's going to end up, this sum is going to end up a small number. And once you normalize it by f to the n, you're going to get, and then take a minus log, you're going to get that the analytic rank is just roughly n. Okay, so for a polynomial in n variables, for a random polynomial in n variables, the analytic rank is going to be n, maximal. We're interested in polynomials that are biased. The other notion is the notion of structure, algebraic structure. So this is usually defined by the notion of the rank of a polynomial. It's simply the smallest number of lower degree polynomials that can be combined to give our polynomial. Okay, so we want to write our polynomial P as an arbitrary function of a small number of polynomials of lower degree. So okay, this is algebraic structure. So our polynomial is in some sense, even though it's of degree 10, but actually it can be described with a small number of polynomials of degree 9. And so the first notion, right? It came up in the context of Fourier analysis, higher order Fourier analysis, right? In Fourier analysis, you're talking about chi of a linear polynomial. Here you have chi of an arbitrary degree polynomial, but we don't have to think about Fourier analysis here. So analytic rank just measures the bias of the polynomial. Rank measures algebraic structure. And then there was the seminal result of Green and Tao, which was later further refined by several authors. And they showed that you can bound the rank as a function of the analytic rank. In other words, if your polynomial is biased, then this can be fully explained by the fact that the polynomial has algebraic structure, can be written as a small number of lower degree polynomials. Okay, so that was Green and Tao's result. It was proved using a kind of a regularity lemma for polynomials. And the bounds that you get, this function f, this dependence, is kind of horrible. It's Ackermann type function. So that's much larger than a tower of exponentials. So you really should think of this result as a quantitative result. Okay, so you can bound, it is possible to bound the rank as a function of the analytic rank, just this function can potentially be horrible. So as you would expect for a statement this basic, it has a lot of applications. So it corresponds to a special case of the Gauss inverse norm, the inverse conjecture for the Gauss norms. It has applications for effective algebraic geometry. It has applications in coding theory and in complexity theory. But all of these applications inherit the Ackermann type bounds, which is quite disappointing. And then the main question that we're talking about here is, can we find a quantitative proof of the structure versus randomness dichotomy for low degree polynomials? One that gives us actually reasonable bounds. So that's the question we're going to deal with. In fact, it turns out that instead of talking about general arbitrary polynomials of degree k, we talk about multilinear polynomials, then there's actually very little loss of generality, very little loss in the parameters. And the question becomes kind of nicer, and we have more theoretical tools. So we're going to do that, which is quite standard. We're going to switch from general polynomials to multilinear polynomials, also known as tensors. So you can think of a tensor, it has actually a lot of useful equivalent definitions. Generally speaking, a K tensor is just a function that takes K vectors and is linear in each vector separately. But let's go over quickly the various equivalent definitions. And for simplicity, let's fix K to be 3. So we're talking about 3 tensors, order 3 tensors. So one way to think about 3 tensors is, as I said, a multilinear polynomial. So you have 3 groups of variables, xi, yi, and zi. And every monomial contains a variable, one variable from each group. So every monomial is of the form xi times yj times zk. Okay, so that's a multilinear or 3-linear polynomial. Alternatively, you can just take all the coefficients of these monomials and group them in a 3-dimensional matrix. Okay, so that's another way to think of a tensor. Or more abstractly, you can think of it as an element of the tensor product of the 3 vector spaces. And the fourth way to think of a tensor, which is I guess slightly less trivial than the other ones and is going to be useful for us. So we're going to move one of the vector spaces into the codomain. So what we're going to do is we're going to view 3 tensor as a polynomial map. So that's a tuple of polynomials. Each polynomial is going to be of degree 2. It's going to be a bilinear polynomial. So how do you get this correspondence? So for k equals 2, this is just the usual correspondence between 2-dimensional matrices and linear maps. Okay. For 3 tensors, how do you get this correspondence? So you start with your 3-dimensional matrix, bottom left, and you slice it along any one of the 3 axes. So you get a bunch of 2-dimensional matrices, and each matrix naturally corresponds to a bilinear map. So what you have here is a tuple of bilinear maps. Okay, so again, you can start with a trilinear form, and then slice it along the x variables or y variables or z variables, and you're going to get a bunch of polynomials, say in the xy variables. Okay, so we can think of every tensor as a polynomial map, and it will be convenient to just call, so the vector spaces vi are just finite dimensional vector spaces over the finite field f. So I'll just call them, I'll just identify them by fixing bases with f to the n for some n, and the codomain I'll call it f to the n. So again, every tensor, you can think of it as a polynomial map from some f to the n to f to the n. Okay, so that's that. So now let's go back to the notions of structure, randomness and structure, and just specialize them to tensors. So if you have a tensor, then the analytic rank, you can you can start with a definition, and it's not too hard to see that it's actually counting for tensors. It actually exactly only counts the number of zeros of your polynomial. So if you carefully do it, you can see that the analytic rank for a tensor is exactly the normalized number of zeros of t when t is viewed as a polynomial map. Okay. Okay, so this is just if you take a uniformly random input and you apply t on it, what are the odds that you're going to get the zero vector? Okay, so that's analytic rank. Partition rank, so that's kind of like a slightly more refined notion of rank if you have a tensor. So when we're talking about a tensor, then we can write it as a sum of lower order tensors, a tensor product of lower order tensors. So again, we want to write T as a sum of a small number of tensor products of AI and BI, which are lower order tensors in disjoint sets of variables. Okay, this is the kind of a special case of the previous definition of rank, where there the T was obtained as some arbitrary function of these AIs and BIs. Here it's a specific function. So it's just nicer to work with this definition. And by the way, for 3 tensors, this is precisely slice rank that Terry Tao defined in the context of the capset problem. So it has nice combinatorial properties. And also, as I mentioned before, there is really little loss in generality when you only talk about multilinear polynomials, when you only talk about tensors. Okay, so if you start with an arbitrary tensor of degree k, you can take its kind of standard symmetrization, and you're going to get an order k tensor, and it's going to have roughly the same analytic rank, and its partition rank is going to be roughly, or bounds from above the rank. Okay, so from now on, I'm just going to talk about structure versus randomness for tensors. Okay, so let's move on. Actually, before moving on, let me give you a very quick example, just to have a running example in mind. So suppose we're talking about this tensor D, which is a 3 by 3 by 3 tensor. Okay, it's an order 3 tensor. And it's just the determinant of the 3 by 3 matrix that you get if you just put, as the rows, you just put the 3 arguments. Okay, so obviously the determinant is a multilinear polynomial. So this is a degree 3 multilinear polynomial. Okay, so this is a 3 tensor. Now, if you want to talk about its analytic rank, then if you remember the previous slide, what you should do is you should slice it along one of the axes. So you should really think of this 3 tensor as a polynomial map, a bilinear map. Okay, so if you do that, maybe you slice along the z variables, then it's not hard to see that the corresponding bilinear map is just the cross product of the 2 vectors x and y. So you have x and y, a pair of 3-dimensional vectors, and the cross product is a new 3-dimensional vector, and that's exactly gives you the corresponding bilinear map. So now if I want to talk about the analytic rank of this tensor, I need to count the number of zeros, right? So I want to find for which pairs of vectors x, y, the cross product is the 0 vector, which is obviously the pairs of vectors who are scalar multiples of each other. And if then, kind of heuristically, if you just count degrees of freedom, right? If x can be intuitively, x can be an arbitrary vector, and maybe the first coordinate of y can also be arbitrary. But once you know these 4 scalars, then right, you know the the scalar relating x and y. So you know the other 2 coordinates of y. Okay, so you really have 2 degrees of freedom, which means that the probability that x and y are scalar multiples of each other is f to the -2 roughly, where f is your finite field. Which means once you normalize that the analytic rank is essentially 2. Okay, so that's the analytic rank. And you can show, and that takes a bit of work, so I won't do this here, but the partition rank of this particular tensor is actually maximal. It's actually 3. So this particular tensor doesn't have any algebraic structure in our sense. You can't write it as a small number of lower order tensors, but it is somewhat slightly biased. Okay. So we have this example. We'll get back to that quickly later. But now, now that we're more or less comfortable with tensors, let's go back to our question. So just in the previous example, we had analytic rank roughly 2 and partition rank 3. And it's not hard to show actually that analytic rank is always at most the partition rank. So that's always true and rather easy. The hard direction is the inverse direction, right? To show that the partition rank is upper bounded by the analytic rank, okay? Just again, the statement that if your tensor is biased, then you can explain it by an algebraic structure that the tensor has. And there's been results over the years relating partition rank and analytic rank. And the conjecture that many authors have made is that maybe perhaps they're actually equivalent up to a constant, right? Up to a constant, multiplicative constant depending only on k, maybe partition rank is equal to analytic rank. So in fact, when k is equal to 2, this conjecture is very much true. It's so true that the multiplicative constant there is actually 1. And that's exactly linear, basically linear algebra, right? So let's see that. So the analytic rank, as I said, is just a normalized number of solutions of the corresponding polynomial map. But in this case, the polynomial map is a linear map. So the number of solutions of a linear map is just the kernel. It's a linear subspace, the kernel of that linear map. And if you properly normalize it, so you divide by f to the n, of course, we know that the size of the kernel over a finite field is exactly f size of the field to the dimension of the kernel. So what we're getting here by rank nullity is just the dimension after you normalize with the log, you just get the dimension of the image of A, which is just the rank of the matrix A. And now you use another equivalent definition of rank, which is the smallest number of rank 1 matrices that sum up to give your matrix, which is exactly partition rank. Okay, so we saw precise equality between analytic rank and partition rank for 2 dimensions, for 2 tensors. Okay, and it used the various equivalent definitions of rank for matrices, of which there are a lot, and it used the rank nullity theorem. When you move to higher values of k, then things become much more complicated. So there have been some works for very small values of k. So when k is 3 and 4, there were some results. So for 3 tensors, Haramati and Shpilka were able to prove a polynomial bound. So the partition rank is upper bounded by some fixed polynomial 4th power of the analytic rank. And for 4 tensors, they proved an exponential bound, which was more recently improved to, again, a polynomial bound. So that's only for 3 and 4 tensors. And going back to 3 tensors for a moment, even more recently, we and independently another group of researchers were able to essentially settle the conjecture, but just for 3 tensors. Okay, so that proof is already non-trivial and very much inspired our current work. But there's actually a very good reason why this can work only for 3 tensors and not for even 4 tensors. So really the question for general K, is quite open. So the breakthrough here, Milishevich and Genzer proved independently that you actually always have, for any K, you always have a polynomial upper bound. So the partition rank is bounded by the analytic rank raised to some constant. So that constant is pretty large as a function of K, but if we think of K as a constant, and this is just a polynomial bound. So that was a big breakthrough, but the conjecture is still open, right? The conjecture is that actually the exponent should be 1 and there just should be a multiplicative constant instead. So that remained open, and that's the main result for today. So we're actually showing that the partition rank is bounded by the analytic rank times multiplicative constant over finite fields of any characteristic, assuming that they're large enough in terms of this constant K, and also in terms of the analytic rank T, which is maybe not so bad, because when in applications, when you want to apply this theorem, you really care about the case where the analytic rank is small, right? The polynomial is biased, and then you get an algebraic structure. Okay, so if you think of analytic rank as small, then this is not such a horrible restriction, and that's it. So under this restriction on the size of the field, not a characteristic, we settle this conjecture. And so partition rank is, as I said, it's a combinatorial notion, and it's not too hard to bound it for explicit tensors sometimes. And the analytic rank has, better theoretical properties. And really what this theorem, this result shows is that in some sense, they measure the same thing. And so what about the proof? So I'll try to use the remaining 35 minutes to say some things about our proof. Generally speaking, we're going to use algebraic geometry, and we're going to use a more local analysis. And that's in contrast to, the green tau regularity type arguments, and also arguments that rely on results from additive combinatorics and kind of a global analysis, which is what was mostly used before us. And perhaps this is the reason why we can get the correct bounds. Okay. So as I said, we will be using algebraic geometry. So any questions so far about the statement that we want to prove?
Do you have any comment about this multiplicative constant? Is this
Is this the right constant you're asking? Is this the best?
Yeah, essentially that.
That so not quite. So already so I think this is off by a factor of 2. That would be my guess. So maybe for k equals 3, it's roughly the right constant. It's essentially the right constant, but for general k, I would say no. I would say we're off by a factor of 2. Yeah. Okay. So that's the statement. So as I said, we're going to be using algebraic geometry. So maybe I'll spend a few slides kind of reminding you of basic terminology. If you've never encountered that terminology, this might be too much information. But if you have been exposed to varieties at some point in your life, then this should be a useful reminder. So first of all, let me explain what I mean when I say total derivative before I talk about algebraic geometry. So suppose you have a rational map. So a rational map is just a tuple of rational functions. A rational function is just a quotient of polynomials. So suppose you have a rational map, you can talk about its total derivative, and it's going to be a matrix. Okay, so if you start with a tuple of functions, the total derivative is a matrix of functions, of rational functions. It's actually the Jacobian of these polynomials. So it's going to be an m by n matrix. M is the number of polynomials. And for each polynomial, you're going to take its derivative with respect to each of the variables. Okay. So again, d of f, that's just the Jacobian of the polynomial map, or the rational map f. And by the way, right, it's a matrix. If you apply it on some vector, that gives you exactly the directional derivative in the direction of that vector. Okay, so that's that. And notice that, so if you take the total derivative, you get a matrix of rational functions, but that's again a tuple of rational functions. You can take the total derivative again. So you can iterate that. And if you iterate it again, you get, so you iterate it twice, you get a 3-dimensional matrix, where each entry is again a rational function. Okay, so just as an example, if your rational map happens to be a polynomial map, every entry is a polynomial, then if you take the total derivative twice, you're getting a 3-dimensional matrix where every entry is a polynomial of a degree which is the original degree minus 2, right? So every application of the total derivative decreases the degree of each polynomial, of the polynomials in each of the entries, but you're getting higher and higher dimensional tensor, or higher order tensor. Okay, so keep that in mind. When I talk about a tensor, sorry, when I talk about the total derivative, we're actually increasing something. We're talking about, we're increasing the dimension. Okay, and of course it satisfies the usual properties of derivatives. A quick recap of some basic notions in algebraic geometry, which I will need. So a variety is just the set of solutions of some polynomials, some finite set of polynomials. And when I talk about solutions, I mean solutions in the algebraic closure. Okay, so we're starting maybe with some polynomials with coefficients over a finite field f. But when we're talking about the solutions, the set of solutions, the variety they cut out, that's a subset of the algebraic closure to the n. Okay, that's what makes varieties geometric objects. The ideal of a variety is just a collection of all functions of all polynomials that vanish on the variety, in addition to the polynomials that cut out the variety. Every variety can be uniquely written as a union of irreducible components, irreducible varieties. Variety is irreducible if you can't write it, if you cannot write it as a union of subvarieties. And the dimension of a variety, you have here the formal definition, but intuitively it makes sense. You can see the figures at the bottom. And the codimension of a variety is just n minus the dimension. So as you can see, for dimension 0, you have just a disjoint. So the irreducible components are just singletons. Dimension 1 is just a union of curves. Dimension 2 is union of two-dimensional surfaces, etc. And finally, we say that a point on the variety is an f point or an f rational point if its coordinates are all scalars from the ground field. Okay, so a general element in a variety is going to have coordinates in the algebraic closure, but if those coordinates happen to all come from actually the base field, then we call this an f rational or just f point. And we're denoting by v parentheses f just the set of all f points in that variety. Okay. Whew, so that's the terminology I need. One last piece of terminology is the tangent space, and that's what gives our proof the local property. So I won't go into the formal definition of a tangent space, but intuitively it's exactly what you think it is. So on the left figure, you have a one-dimensional variety, a curve. You choose a point, and in blue you have this tangent line. So this is the tangent space. It's a one-dimensional space. Affine or vector space, doesn't really matter. On the right figure, you have a variety in yellow, a two-dimensional variety. You choose a particular point there, and you talk about its tangent space. This is going to be a two-dimensional vector space. Why two-dimensional? It corresponds to the fact that the variety itself is two-dimensional. As opposed to, by the way, if you take a look at the left figure and you choose the origin as your point, then you actually have not just one line, which is tangent, but two lines, or rather a whole a vector space of dimension 2. Okay, so in this case, the origin is a singular point on that variety. So a typical point on a variety is not singular. So singular means that the dimension of the tangent is strictly larger than the dimension of the variety. A typical point would have equality. Okay, so that's all I will need, all the relevant background. Now I can talk about kind of the rough structure of the proof. Okay, so as I said, our first step is going to be to move to the algebraic closure. Seems counterintuitive because the question is about finite fields, but we're going to do this nonetheless, just so that we have the tools of algebraic geometry at our disposal. So we're going to have two parts to our proof. The first part is the upper bound, second part is the lower bound. So let's talk about the first part. First, what we're going to do is start with our tensor T, which we view as a polynomial map. and take a look at and consider its the Jacobian, or the total derivative. So if you remember, the total derivative of a polynomial map is a polynomial two tensor, right? A polynomial two-dimensional matrix. So again, it's not a single matrix, it's a matrix of polynomials. So it's a whole family of matrices, if you will. And so what we're going to do is we're going to find a partition rank decomposition for this tensor. Again, it's an order 2 tensor, but it's an order 2 tensor of polynomials. So we're actually going to find a rational map that that decomposes, that gives you this partition rank decomposition almost for any input x. Okay, so almost for any x that you plug in to this matrix would give you a matrix of scalars that we have a partition rank decomposition for. And this decomposition is given by some rational map. So we do this using algebraic matrices, Kramer's rule, kind of a rational version of that. So that's actually going to be the base case of our inductive argument. So we start with this two tensor where we have this partition rank decomposition, and then, and maybe this is the core of our proof, we're going to lift it. So what we're going to do is to show how if you have a decomposition of some polynomial map, then we can construct a decomposition of its total derivative. But its total derivative is a tensor of, right? It's going to be a 3 tensor, and then iterating this a 4 tensor and so on. Okay, so we're going to have this lifting theorem which says that if you have a rational map that gives you a decomposition, then you also have a rational map that gives you a decomposition of the total derivative. Importantly, this all happens on some open set of some variety. Okay, so this happens in the context of some variety, and actually the proof is quite flexible, so we can take the variety X to be, basically any variety that you want. And finally, so you apply this lifting theorem, you iterate. At the end of this process, you're going to end up with a partition rank decomposition over this variety for dk minus 1t, so the total derivative of t of order k minus 1. But since t was a k tensor, which means that every entry in this polynomial map was of degree k minus 1, that means that you end up with a k, okay, so you start with a k tensor t, and you end up with a k tensor, but every entry in this k tensor is going to be a polynomial of degree 0, so a constant. And it's not hard to show that you can actually use that k tensor. If you have a partition rank decomposition of that k tensor, then you get 1 for the original k tensor. Okay, so you kind of cycle, right? So you take total derivatives again, until in some point you, in some sense, cycle back to the original tensor. And since we have partition rank decomposition throughout the process, then we also have a partition rank decomposition for the original tensor we started with. So that's basically the first part of the proof. That gives us an upper bound of the partition rank, right? We find the partition rank decomposition. The issue here is that all of this happens over some variety. And so the partition rank decomposition that we obtain can very much happen to be over the algebraic closure. Okay, so we will end up with a partition rank decomposition of T, but every summand can be tensors not over the base field, but over an extension field, which is not at all what we need. Okay, so that's not the end of the story. And there comes the second part of the proof. So what we're going to show is that we're going to construct a particular variety X for which we can guarantee that the partition rank decomposition we found in the first part is actually over the base field. Okay, so that requires a particular choice of X that wins. So it's a particular variety that we construct. Okay, so these are the two main parts. The first part is an upper bound on the partition rank. The second part is a lower bound on the analytic rank, and they're going to match. Okay, so that's the very general strategy. But notice that right? I'm talking here about analytic rank, but I'm also walking over the algebraic closure. And that doesn't really make sense, right? Because analytic rank is by definition a notion over finite fields. There's no analytic rank for infinite fields. Luckily, there is a geometric analog of analytic rank that does the job for us. So this is called the geometric rank. So whenever your field is algebraically closed, you can talk about the geometric rank of your tensor, and it's defined as follows. So what you do is you consider the kernel of T. So again, you view T as a polynomial map, and then you consider the set of solutions, the set of zeros of this polynomial map. This is just the kernel of T. Of course, if T is a 2 tensor, then the kernel of T is just the usual definition from linear algebra. And then we take the codimension of that, and by rank nullity, the codimension of the kernel is exactly the rank, the rank of T. For 3 tensors and above, really what you have here is the codimension of some variety. Okay, this variety is cut out by polynomials of degree k minus 1, right? Because these are the entries of this polynomial map. Okay, so we start with a k tensor that gives us a kernel variety, and it's an algebraic geometric object, and then you can talk about its codimension, and that's the geometric rank. And as I said, when k is equal to 2, the kernel of T is just the usual kernel, and so the geometric rank is just the rank by rank nullity. On the left figure, you see an illustration of a kernel for a 2 tensor. So that's a linear subspace. It's a flat variety. Generally speaking, the kernel is more interesting. It can be a very complicated variety, even for k equals 3. And if we go back to this running example that we have, right, the tensor whose corresponding map is x cross y, then the kernel are precisely all the pairs xy whose cross product is the 0 vector, which we know is just means that they're scalar multiples of each other. And again, by essentially the same argument from before, but now not over any particular finite field, but using algebraic geometry, you can see that the geometric rank, the codimension of this, the number of degrees of freedom, quote unquote, is 2. Exactly 2. Okay, so the integer 2 as opposed to approximately 2. So that gives you a sense of why the geometric rank is the analog of analytic rank. But what's kind of like, in general, what's the reason? Not for any particular example. So if you remember that the definition of analytic rank is just this, the normalized number of zeros. But you can think of, right, the set of zeros, this is just the kernel of T, but just the set of f points, f rational points, right? The points in the kernel, right? All the points from the algebraic closure that are zeros of all these polynomials, except we want these points to be from the base field actually. Okay, so this is the ker T parentheses f, the f rational points from the kernel. And if you rearrange that, you get n minus and just the normalized number of f points of the kernel variety. Now, if the kernel variety is a linear subspace, then we know that its size, or the number of f points, is just the size of f to the dimension of the kernel. And then once you take log and n minus, rank nullity gives you that this is just the codimension of the kernel. Okay, but if the kernel of T is not a linear subspace, then of course this is a general variety, but more general variety. But the thing is that, at least kind of intuitively, Schwarz-Zippel for varieties or the Langmuir bounds tell you that you would expect here that this number is going to be the size of f to the dimension of the kernel still, but now it's the dimension of a variety, not the dimension of a linear subspace. And so this shows you that you would roughly expect the analytic rank to be equal to the codimension roughly, but that's of course all kind of like hand waving. But that's supposed to convince you that analytic rank or geometric rank is the analog of analytic rank over algebraically closed fields. Okay, so let me give you the proof outline, and if you follow this, then I did my part. So let me just give you the gist of it. So we will need one important definition. So for a variety V, we're going to define dim sub f. So f is going to be the finite field. V is a variety, so it lives over the algebraic closure. Dim sub f is going to be defined as follows. So looking at the largest dimension of a subvariety Z, so a subvariety of V, but also one that contains all the f points, with the following property, I want it to have a non-singular f point. Okay, not just a non-singular point, because every variety contains non-singular points. I want there to be a non-singular f point on a top dimensional component, which is also defined over f, so cut out by polynomials over f. Okay, you can think of it as some kind of a generalization of the notion of dimension when we're talking about some base field which is not algebraically closed. If f is algebraically closed, then this definition reduces to the usual definition of dimension. Okay, and also I underlined the word non-singular because we're actually going to use, we're going to need a slightly more general notion of non-singular, but let me not talk about that. So here are the two statements that underline the first part of the proof and the second part of the proof. And for the rest of the slide, T is a K tensor over a perfect field. The perfect fields contain the finite fields and algebraically closed fields in particular. So essentially every reasonable field that you can think of is a perfect field. So there's very little loss of generality here. So the first part essentially says the following: we're going to bound the partition rank of this tensor. Of course, the left-hand side denotes a partition rank decomposition over the base field, over the finite field. So we're going to bound it by some constant times this codimension sub f. Okay, so codim this is just n minus dim sub f. Okay, so this is not just the codimension of the kernel, but the codimension sub f, this new definition of codimension. It's a larger number actually, okay, because dim sub f is smaller than dim, which means that codim sub f is larger than codim, generally speaking. But this is how we will be able to bound the partition rank. And of course, an immediate corollary is that if f happens to be algebraically closed, then we know that codim sub f is just the usual codim, aka the geometric rank. So that gives us a bound, an upper bound. Partition rank is at most a constant times the geometric rank, which can also be shown to be, the geometric rank can also be shown to be at most the partition rank. So that gives us an equivalence of partition rank and geometric rank up to a constant. That's great, but that's not quite what we want. We want to relate partition rank and analytic rank, right? We care about finite fields. This is the question. And so the second part is going to be a lower bound on the actual analytic rank, not geometric rank. We're going to show that it's actually lower bounded by, again, the same notion, codim sub f, with some error term that depends on the analytic rank and k. But if f is large enough, again, not the characteristic of f, but just the size of f, then this becomes a negligible error term, and the upper bound from the first part and the lower bound from the second part coincide up to the constant. So that's that. These are the two statements and whose combination completes the proof. So maybe I'll spend the next 10 minutes giving a sense of why the first part is true. But any questions so far? Okay, then let me say a few words about the upper bound. If I have time, I'll say something about the lower bound, but we'll see. Okay, so I'll go pretty quickly over this. A very quick detour. So we're going to work here with rational functions that give you partition rank decompositions. So to be able to do math with that, we need to parameterize the space of all partition decompositions. We do that by thinking of them as two lists of lower order tensors. So let's immediately jump to an example, because otherwise this might seem a bit abstract. So we're talking about the constructing space for three tensors. So here's a concrete example here in yellow. On the first list, the first item in the first list is this polynomial in the x variables. But you have, for three tensors, you have x variables, y variables, and z variables. So the first item in the first list is a linear form in the x variables. And then the first item in the second list is a bilinear form in the y and z variables. You multiply them both. You multiply the first from the first list and the first from the second list, plus a linear form in the y variables times a bilinear form in the xz variables, plus a bilinear form in the xy variables, never the z, times a linear form in the z variables. Really, every partition rank decomposition looks like that. A sum of, right, these are all the possible ways to get a partition rank decomposition, right? The x variables can be in the first multiplicand, and then the y z variables in the second, or all other combinations. In this case, you have three possible kind of combinations, or I should say partitions. And so this corresponds to three summons, and the R constructing space is just R guys like this. So R lists of these guys. Okay, just a way to parameterize partition rank decompositions. How do you get, formally speaking, how do you get from these two lists, how do you get back a tensor? You just apply this inner product function on tensors. So you just sum the first item from the first list and the first item from the second list. Oh, sorry, you take a tensor product plus the second and the second, etc. So all of this is to say that, and we have this very kind of not deep remark, but still, if you can put your tensor in the image of this inner product map function applied on the R constructing space, then that immediately gives you a partition rank decomposition over the base field whose length, the number of summons, is R times a constant. Why this? So this constant for k equals 3 is just 3. Whereas in general, what is this constant? This is just the number of bipartitions of k things, right? A non-trivial bipartition and also unordered. That's the number of ways to, that's the number of possible partition rank terms. Anyway, bottom line, we will be talking about, our goal will be to put our tensor in the R constructing space for a small r, and that would give us a partition rank decomposition. Okay, so here's the core of it, the inductive step, the lifting theorem. And by the way, just a tiny piece of notation, whenever you have rational maps f and g, and maybe some variety x, then we will say that f and g agree on x if they return the same value for every point in the variety where they're both defined. Okay, so that's the notation. Here's the lifting theorem. So it's a bit of a mouthful, so let me just emphasize the important things here. So the inputs to this theorem, there are two of them. First of all, an irreducible variety defined over f. So this variety x. And the second input is some polynomial tensor. Okay, so it's d-dimensional matrix where every entry is a polynomial. This would represent, the various, the iterated derivatives of our original tensor. But anyway, here's the thing. The assumption in this lifting theorem is that you have, so this is the assumption in yellow, restricted to this variety x, you have at every or almost every point on that variety, you have a partition rank decomposition of f. So again, if you plug into this polynomial tensor, you plug in inputs from the variety x, then for almost all, almost every point in the variety, you can write this as IP composed age. So age just gives you these two lists, right? Age just specifies the partition rank decomposition. And of course, once you apply this inner product, you get back your tensor. So again, age specifies the partition rank decomposition at any point in that variety. And this just goes to say that we have a partition rank decomposition in an open subset of the variety X, given by some rational function H. Okay, so H is a rational function. Oh, sorry, I should say a rational map. Okay, it takes a vector X and returns these two lists of tensors. So it takes a bunch of scalars and somehow returns two long lists of tensors. So this is the assumption in this lifting theorem. The guarantee is that the derivative of f, which is a tensor of higher dimension, of higher order, I should say, also has a partition rank decomposition restricted to the same variety. Okay, so there's another function, rational map H prime that now actually returns two lists in a constructing space of d plus 1 tensors. And the S here, so it's the S constructing space for bounded S. So we can bound S by the maximum between R, which was the length of the decompositions that in the assumption, but also what enters the picture is the codimension of X. Okay, so the geometry of the variety enters the picture, enters the partition rank decomposition here, right? That's the codimension of X, which bounds the length of the new decompositions. Now this, again, this can seem a bit much, but it might be easy to kind of look at the corresponding commutative diagrams. So on the left, you have the assumption in the statement. So you have your variety X. For almost every point in X, you have a rational map that returns partition rank decomposition, which means that if you apply the inner product, you get a genuine tensor, namely the tensor F, but only restricted to X. So if you have this scenario, if you have this setting, then this lifting theorem tells you that over the same variety, you have H prime that gives you a partition rank decomposition of tensors of order d minus 1. Not for F, of course, but for the derivative of F. So this is the kind of the engine that makes everything work. As I said before, you start with your tensor, which you view as a matrix. You manually construct a partition rank decomposition by a rational map for that one, and then you apply the lifting theorem, which gives you a partition rank decomposition restricted to that variety of the second derivative and the third derivative and so forth. At the end, you're going to cycle back and get a partition rank decomposition for your original tensor. So let me just give the intuition where this is coming from, where the proof of this lifting theorem comes from. So for every point on the variety where H is defined, so where we have, so in yellow, we have our variety X. At every point on that variety, we have the polynomial map F, it gives something. Okay, so for every point on the yellow surface, we have F of X there. If you take an X for which we have a partition rank decomposition, then if you take the derivative of F along vectors that are in the tangent space, then, and this is a kind of a semi-standard thing, you can show that the derivative of F is given by the derivative of IP composed H, right? Because F by assumption can be given by this composition of rational maps, then so does the derivative restricted to tangent vectors. So that's the first part. But of course, I'm reminding you that df is a linear map. So we know how it behaves. We can control it over or restrict it to the tangent spaces, but what about the rest of the space? So it turns out that for non-singular points on the variety, we can decompose the entire space into the tangent space at that point and some complementary subspace. All of that using some rational map. And then you can show that for these non-singular points, kind of trivially, you get a partition rank decomposition whose length is just the dimension of this complementary subspace. That's easy enough. But the thing is that if you remember that at non-singular points, the dimension of the tangent space is equal to the dimension of the variety, which means that the complementary subspace is of dimension codim of the variety. Okay, so this is the main term of our decomposition. This is, if you call it a second or remainder term. And you can show that if you put those two together, these two decompositions together, they live in separate parts of the constructing space, right? The terms there are kind of disjoint. And so putting them together gives us H prime. Okay, and this is what the locality comes from, right? So the main term of our decomposition comes from taking the derivative of F along tangent spaces. So right, it's a very local thing. Okay, so I think I'll stop here. I think I gave you a gist of at least the upper bound, so you got something. Okay, thank you.
Thank you very much. Why don't we all unmute and give Guy a round of applause? Does anybody have any questions for Guy? So are there any wrinkles in small characteristics? I think everything holds for, you said for fields that are sufficiently large.
No, so everything works for any characteristic, even characteristic 2 should be.
Okay. I was wondering what's very early on in the talk when you mentioned the symmetrization trick, just from getting from arbitrary polynomials to tensors. Is that restricted to?
And that's a good question. Actually, fantastic question. That actually, I should write this. This actually assumes that the characteristic is at least the degree of the polynomial, or greater than the degree of the polynomial. So that's true. So that's maybe the nicest thing about switching. Right? If you remember, we started with talking about the general problem for general polynomials, and then moved to restricted only to tensors. That's maybe the best reason to do that. That's because for tensors, we don't have these issues of low characteristic. So when you talk about tensors, everything works in any characteristic. If you want to make the switch to arbitrary polynomials, then you need the characteristic also to be large enough.
And so in your result, you assume that the field is sufficiently large in terms of the analytic rank and the order of the tensor. Is it reasonable to say what that function is?
So it's a double exponential function, which is maybe not too surprising if you talk about algebraic geometry. This is the types of bound that you tend to get. Yeah, so it's a double exponential. I'm not actually sure whether there's any hope of improving this or not. Maybe, just maybe. Probably not using these methods.